Let us continue. So we can say that an absolute value W pump is V. Why here they consider the positive value? Because look, they are putting for W, okay, for W pump in, okay. So they consider that when they will replace after, okay, they will do minus W pump in, okay. This is why they put V P2 minus P1, okay. So uh, we are done with the work of the pump. So to find the work of the pump, all you need to know is what are P1, P2, and the specific volume, okay. And for the specific volume, you can get it from the tables. So we will do a lot of examples on this. You go to the tables, you say point 1 is on the saturated liquid curve. So I will take for the specific volume the value at the saturated liquid, and I, in general, P1 and P2 are given, so I can find the work in the pump. Once I find the work in the pump, I can apply the energy equation for the pump. For the pump, what is happening? I don't have a heat loss. I have only energy exchange through work. Okay? So I can write that for the pump, and of course, I neglect variation in kinetic and potential energies. Okay? So I can say that for the pump, if I apply the energy, no Q, Q is 0. So I have W is equal to a variation of enthalpy, H2 minus H1. Okay, if you want, I will go back to the general rule. So always you go to the general rule here, and you can simplify it a lot depending on the application. You remember this law? This law, we will use it in all our energy, in all our cycles when we do energy analysis. So here, this equation, what it's telling you that Q dot of the heat exchange in the control volume with its environment, okay, plus m dot inlet, okay, times the energy at the inlet equals to m dot times outlet energy plus the work done by the control volume, okay. So you can see here in the compressor, what is happening in your compressor? In your compressor, no heat, so this term cancel out, okay? If you assume no variation of kinetic, and as I told you last time, in general, when you have a fluid circulating, in general, if they don't give you any information, you can consider that the kinetic energy and potential energy are very small compared to the enthalpy, so you can neglect them, okay. So you end up here for the pump, you end up with the work in the pump, so W pump, okay, is equal to m dot times h1 minus h1 minus h2. But why they put in their calculations, they put h2 minus h1? Because they are taking the absolute value, okay. But when you do m dot h1 minus h2, you will have a negative result, and this means that your pump is taking work from outside. It's not producing work, okay. So if you put minus W pump in your calculation, then W pump will be m dot times h2 minus h1, okay, because it's a work that is going inside your system, not produced by your system. So if I go back, so the whole idea is to apply this formula for all the components of your system: the pump, the turbine, the boiler, the condenser. Okay. So if we go back to our cycle here, okay, then as you can see here, because they are just putting after minus W pump, they are taking here the absolute value. which is H2 minus H1. Okay, now for the boiler, what is happening in the boiler? As we said, in the boiler we have exchange of heat and no work. Okay, so for the boiler you can say that Qn is the difference in enthalpy between 3 and 2. So also going back to the previous equation, okay, no work and negligible variation of kinetic and potential energies. So you can write that the boiler heat that is entering my system Qn is the difference between enthalpies at point 3 and 2. So it's H3 minus H2. Okay. Now for my turbine, what is happening? I am producing work. Okay. So this is a positive work for me. This is why for the turbine I write like the compressor, the same equation. Okay. And I end up for the turbine that W turbine is equal to H3 minus H4. Okay. And finally, for the condenser, what is happening in the condenser is that I am losing heat. Okay, so I have Q out is the difference between H4 and H1. Just a small note for you, because here they are considering only the absolute values. So this is why they are taking, if you want, for the pump they take H2 minus H1, while if you want to have it with the sign, you should do H1 minus H2, inlet minus outlet. Okay, but they did the opposite because they are taking the absolute value. Since as you can see after here, they are putting, when they consider the nets, they put minus. So W turbine minus W pump, and here Q inlet at the boiler minus Q at the condenser. Okay, if you don't want to do this, it's not a problem. If you can apply the equation above as it is, so you get here H1 minus H2, and it will be negative. Then you don't have to do, if you do this, you don't have to put here a minus, you just put a plus. Okay, and the same for Q out. If you apply the formula we did together above, you will have H1 minus H4. Okay, so you will get a, and you will get a negative result in this case, which is the case because you are losing heat in your condenser. Okay, so in order to practice more on these issues, okay, so that you can understand more, I will start doing some problems together, and we will see how we can determine these values. What are the tables that we should use to find these values? So before completing the course material, I will start with you to do some practice on simple problems. Then we move to a complete cycle. Okay? So I already posted the problems for you, and I will post also for you an assignment on this chapter so that you can practice for the exam. Okay? Now for the assignment, I don't want you to send it to me because I just, it's for your for your advantage to do it. You are graduate people, and you are you know enough what should you do. It's not an assignment, so no need to copy, no need to just send it without concentrating on it. All I want you to do is to understand more the material. So please try to do the problems, and if you face any issue, you can directly text me and ask me questions. Okay, because sometimes it seems for you that you understand, but when it comes to practice, you might find some difficulties. So try to do them. It will be a good practice for the exam. Now I will start by problems. Okay, so in these problems, first we will see how to apply the second law of Newton second law of thermodynamics on simple components. Okay, and after we will see how to apply it in cycles. So first we will deal with the heat exchanger. The heat exchanger is like what in the cycle, in the power cycle? It can be in the place of or the boiler or the condenser. Okay, Because at the level of boiler and at the level of condenser, what is happening? You are having exchange of heat between two fluids. In the boiler, your fluid is gaining heat. In the condenser, your fluid is losing heat. But the concept is the same. You are using a heat exchange. Okay? So, consider a water-cooled condenser in a large refrigeration system in which R134A, this is the name of a refrigerant, is the refrigerant fluid. The refrigerant enters the condenser at 1 megapascal and 60 degrees at the rate of 0.2 kilogram per second and exits as a liquid at 0.95 megapascal and 35 degrees. Cooling water enters the condenser at 10 degrees and exits at 20 degrees. Determine the rate at which cooling water flows through the condenser. Okay? So let us write first. It's very important to write our boundaries, to know what are the inlet conditions, what are the outlet conditions, to be able to write the second law of thermodynamics, and the first law of thermodynamics, and do the corresponding analysis. Okay, so you have first here the information that you know is that for your refrigerant, this is your refrigerant inlet. You know P inlet is equal to 1 megapascal. Okay, and it's entering at 60 degrees. At 60 degrees. As you can see here, they didn't mention, for example, what is the state, because once they give you pressure and temperature from the tables, you can know what is the corresponding state, and we will see together how. Now, it's exiting as a liquid. So for the liquid, they gave you the state. For the exit, okay, you have a liquid at 0.95. So P out is equal to 0.95 megapascal, and we have a temperature T out. If you want, we can add R, because for the refrigerant, because we have also water. So PR outlet and TR outlet are given. Okay. So we know the inlet and outlet state of the refrigerant, and also we know the inlet and outlet state of water. So cooling water, so here water is in the liquid state, and because they just mentioned, so it's liquid in the inlet and outlet, but at the inlet it is at 10 degrees. So T water inlet is equal to 10, and T water outlet is equal to 20. Okay, so now I want to find what is the mass flow rate of water. Okay, so the first step in this problem is to write the first law of thermodynamics, which consists of the conservation of energy. Okay, and see what are the only unknown will be for me the water flow rate. Okay, but in order to find the water flow rate, I should compute the enthalpies at the different states, because you know that if I write the first law of thermodynamics, let us see it here. Okay, so we just apply the relation we have seen together in here. So always go back to this relation. Okay, this is the main relation you will use. This one. Okay, you have here in this problem, in the heat exchanger, what are the terms that will cancel out? First, in a heat exchanger, you have exchange of heat, no work produced, so this term will cancel out. Okay, And also, as I said before, when they don't mention anything about potential and kinetic energies, you can neglect them. Okay, but pay attention here. You should not use this one. You should use the previous one. Why? Because you have several inlets. When you have several inlets or several outlets, you should use this relation, not this one. This one is only for one inlet, one outlet. Okay, but for the heat exchanger that we have seen here, you have two inlets and two outlets. So I will use this relation. And as we said, no work. Okay, work is 0, so it will cancel out. Okay, and if I consider the system, the whole system of the heat exchanger, then heat is exchanged between the two fluids. So the amount that one of the fluid will lose will be equal to the amount that the other fluid will gain. So what we will say about Q, also Q will be 0 for the total system, because I'm considering the two fluids in one system, not one of them. Okay, you can take the water separately and the refrigerant separately, but it will add for your calculation, because you will need two equations to end up with your result. So it's the easiest way here to get rid of the heat exchange between the two is to take the whole system of the two fluids. So you will have two inlets, two outlets. And this is what we did here. Okay, so going back to the problem, we choose the best idea here is to take the control volume, including the two fluids, like this. Okay, because as I said, if you don't include the two fluids, you will add an additional unknown, which is the transfer heat rate between them. But when you take both, then you have one is giving Q and one is taking Q. Plus Q minus Q will cancel each other. So you can say that the first law of thermodynamics for this heat exchanger can be simply written as follow. So you have some m dot inlet H inlet equal to some m dot outlet H outlet. So the idea now, the whole idea to be able to solve this problem is to find what is the enthalpy of the refrigerant at the entrance, what is the enthalpy of the water at entrance, and what are the enthalpies of water and refrigerant at outlet. So I need to determine these four numbers to be able to find m dot water. Okay, to do this I will go now to tables, and here you need two types of tables. You need tables for water and you need tables for the refrigerant R134A. Okay, and to help you, I already gave the table here, but I will tell you how to search for them. Okay, now as we said, for the inlet state of 134 in the given, they didn't mention if it's vapor or what, but I can do an assumption. I can assume it's a vapor. And how can I verify this? I can go to tables, okay, and I can look at the case of saturated water, and I can look at superheated refrigerant R134A. Because if I assume, so here, what is my assumption? I assume that the inlet of refrigerant, that at inlet I have superheated state. Yani I have vapor. This means that I have vapor. How can I make sure of this? Okay. What are the conditions given for the refrigerant R134A? So always look, when you look at a table, you should look here. This will give you the description. This is for R134A, and this is for superheated. So it means that I am dealing with vapor phase. To verify this, the condition at inlet for the refrigerant are 1 megapascal. So I have 1 megapascal 60 degrees. If I look in this table, okay, look here, when you are dealing in the superheated region, they give you the temperature as inlet and you have pressure here. So you have several pressures, they compute the different thermodynamic values. What you are interested in here is 1 megapascal. So 1 megapascal corresponds to 1000 kilopascal. Okay, and always near the pressure, they tell you what is the corresponding saturated temperature. So for 1000 kilopascal, the saturated temperature is nearly 40 degrees. But what you want is 60 degrees. This means that you are in the superheated region. Why? Because 60 is higher than 39.37. And as you can see here, you can find that for 60 degrees and 1 megapascal, the value of the enthalpy is 441.89. Okay, if your assumption was wrong, it's not a problem. So for example, if the temperature is 30 degrees and you go to the table of superheated R10340A, you can see here that 30 is smaller than the saturated temperature, which is 39.37. So you can say, so I am in the saturated phase. So I am in saturated phase and I should look for the quality. Okay, so I should find the quality and we will see how to do it. But here you don't have this problem because you have found your result in the superheated region. So I should find the quantity. Okay, so now we don't have this problem. Our assumption is right. The inlet is in the superheated region and we got the value of H. So this represents H refrigerant at inlet. Okay, now at outlet, what were the conditions for outlet? They told us that it's a liquid. Okay, it is exiting as a liquid at 0.95 megapascal and 35 degrees. So I should go to tables, okay, and I should try to find the table for R134A in liquid zone or in saturated zone. Okay, so it depends on what I can find in the thermodynamic tables. So here, okay, in some cases, okay, when you have a liquid, you have what is called compressed liquid tables. Okay, but sometimes if they don't give you compressed liquid tables, this means that you can assume if you have a liquid, okay, if you have a liquid state, you can assume that I can go to the saturated table and take the value at saturated liquid. Okay, so I repeat, in general, they give you compressed liquid tables and saturated tables. But sometimes if they don't give you the compressed liquid table, okay, so here, for example, they just give us the saturated table, then you can take that the value will correspond to the saturated liquid value, assuming that it will be close to the compressed liquid value. Okay, so here at the outlet, they gave us, what were the conditions at the outlet? They told us that the pressure is 0.95 megapascal and the temperature is 35. So look here, 0.95 megapascal is close to 0.95 megapascal is nearly 950 kilopascal. It is close to this value, which is nearly 900 kilopascal. So our assumption can be done. We can assume that we can take the saturated liquid value. Now, if you have in the tables what is called compressed liquid, then it is more accurate to go to the compressed liquid table. But if you don't have it, as I told you before, you can take the value for saturated liquid. Okay, so here, if you take the saturated liquid HF and you consider the temperature line 35, the intersection between them will give you HR out, which is 249.1. Okay, now we still have to find the properties of water, because I told you that you have water, liquid water. Okay, 10 degrees and 20 degrees temperature. So now for liquid, okay, you can, for water as a liquid, you can go to the table of saturated water, okay, and for 10 and 20 degrees, you will find your the values of HF, okay, which are 42 nearly and 83.94. What I want to tell you is for water in general, they provide compressed liquid tables, okay? But here, since they didn't give you, yani the pressure here is nearly atmospherical pressure because they didn't mention anything. So that when they don't mention anything, then you can consider that it's entering and leaving at nearly low pressures, okay? This is why you will not find these values in compressed liquid, because in compressed liquid in general they put values for very high pressures, okay? So you will go to the saturated table and look at values of H at 10 degrees and at 20 degrees. You can find them here, as you can see. So I take the 10 degrees line, the 20 degrees line, and for the column of HF, I find that HF at 10 degrees is 42, and HF, which is enthalpy at saturation liquid, is 83.94. Now I have all enthalpies of the four states. So all I have to do now is to go back to my first law of thermodynamics, okay, and replace back the different enthalpies. Then my only unknown will be the mass flow rate of water I can calculate. Okay? Any question on this? Please, if something is not clear, ask. Okay, so let us now take another component, the analysis of another component, which is the turbine. Okay, the mass flow rate into a steam turbine is 1.5 kilogram per second, and the heat transfer from the turbine is 8.5 kilowatt. The following data are known for the steam entering and leaving the turbine. Okay, so in general, for a turbine, always the inlet state is superheated vapor. Okay, so at least you know that at the inlet you should go to the superheated tables. Now, for the outlet, it depends on the cycle. Okay, you can have a point just at the saturated vapor or little bit inside the curve. So in general, you should look at the saturated tables when you want to look at the outlet conditions. Okay. Now here, for example, I told you that at the exit, you have X. X is the quality. X exit is 100%. This means that I am just at the saturated vapor point. So I will go to the saturated tables to get H vapor at this point. Okay. Now we want to find uh, what is the question? The power output. Okay, we want to find the power output of the turbine. In order to do this, we will write the energy, the first law of thermodynamics. Okay, but here pay attention for something. Here, as I told you, if they give you information about kinetic energy and potential energy, you should use them. So here, as you can see in the given, you have m dot inlet, you have the pressure, you have the temperature, but also they gave you velocity and elevation. The same for the exit. So when they give you the values, it's true that they might be negligible compared to H, and we will see in the calculation that they will be negligible. But because they gave us this information, we should use them. Okay? So now, if we go back to our formula and we apply it, okay, we get that the following relation. We have that for this control volume, which includes the turbine, we have the heat provided to the control volume plus m dot inlet times the energy of the inlet state, which is H inlet plus velocity at the inlet square over 2 plus G Z1 equals to m dot is the same because you have conservation of from continuity equation, the mass flow rate that is entering is equal to the mass flow rate that is exiting the system. So it's m dot times the energy. This term represents the energy of the outlet, which is equal to the enthalpy at outlet plus the kinetic energy is calculated through m dot times v square over 2 plus the potential energy through m dot times gze plus the work done by the turbine. Okay, now if you go back to the given, they told you that I have a certain heat lost by the turbine, and the heat transfer from the turbine is 8.5 kilowatt. In general, if they don't mention anything about heat transfer from the turbine, you consider that it is well insulated and we don't have any loss of heat. But here, because they mentioned that we have a certain loss of heat, then we should include it into our equation. And the loss of heat is equal to 8.5 kilowatt. Okay, so now if I go back to the formula, because it's a loss of heat, it is a minus. So I put minus 8.5 kilowatt. Now please pay attention for the units. Okay, so if you are using Q in kilowatt, then also when you replace H should be in kilojoule per kilogram. And if you have Q in watt, then you should replace H in joule per kilogram. So always pay attention for the units. Okay, now Q dot control volume is given. V inlet, Z inlet are given, V outlet, Z outlet are given. So I just need to find the work produced by the turbine. I want to find W dot of turbine, which is this term. And in order to find it, I should determine what is the enthalpy at the inlet of the turbine and what is the enthalpy at the exit of the turbine. So I need these two informations. Okay, now for the inlet, as we said, it is in the superheated region, because always for the turbines we have initially it's steam. So now we will go to see what are the given at inlet. At inlet we give the pressure and the temperature, 2 megapascal and 350 degrees. So I should go to tables and look where do I have the table of superheated steam for 2 megapascal. If you go to your tables, you should look at superheated vapor water, and you have several tables. You should look for the 2000 kilopascal. It is here, okay? And as you can see, as predicted, okay, the temperature here is higher than the saturated temperature, which is 212.42. Our temperature at inlet is 350 degrees. So what we will do is the following. We will go to 350, it's here. We take this line, and then we want to find what is the enthalpy, H. So it is, we can read here that the intersection between the two is 3136.96. So this is H inlet, okay? Now for the outlet, if you go back to the given, they told you that for the outlet, you have a pressure of 0.1 megapascal, and the quality is 100%. This means that you should take H vapor, okay, Hg. So if you go now to, you should go to the saturated table because you have equality. So you are just in the saturated table. If we go to saturated table of water, so here no, it's we are still in the superheated table. This is, yes, 1 second, let me check. So I don't know if maybe the table by error is not here. Yes, one thing, you can say that for the outlet of the turbine, if you want, you can get it also, and you can get it from two states. You can get it from the superheated table, or you can get it from the saturated table. You know why? Because even in the superheated table, they give you the value at saturation. Okay, so as you can see here, for 0.1 megapascal, which corresponds to 100 kilopascal, you can read the value of saturation, because what is the value of saturation? It's equal to Hg. Okay, so here you can find Hg by two methods, or you go to the superheated table and just you read the value at saturation, and you are here in the case of saturation because you have the quality is equal to 100%. So you can read the value of H corresponding to saturation. It's equal to 2675.46. Okay, now if you want, let us use the second method. How to find this value using not the superheated tables, the saturated tables. I will search with you to see the method. So let us go to the tables. Anyway, I will post a link of this book for you. This book is on fundamentals of thermodynamics. You can find all tables at the end of the book. I will post a link for you so that you can download the book and use the tables, because you should have these tables. Okay, so let us see together how to find this another way.
ما عم برد هذا.
Okay, so I should go to water tables. Okay, I should go to water tables, and as you can see in water tables, I have a saturated water pressure entry and I have saturated temperature entry. But here, because I have the pressure, the given is the pressure. Okay, then I will use, maybe they gave us also the temperature, so you can use any of the two, or the pressure here or the temperature. So since the inlet pressure is 0.1 megapascal, so let us look here. It corresponds to 100 kilopascal. So for example here, okay, for this table, as you can see, they give you the specific volume and the internal energy. We don't want this, we want the enthalpy. So we will go down. Okay, here for example, it's for saturated water pressure and entry, and we have the enthalpy values. So now we can search for the 100 kilopascal. So this is the 100 kilopascal here. And I want to take Hg, I want to take the saturated vapor value. Okay, so Hg, which corresponds to a quality of 100%, it will give me that H is 2675.46. So if I compare with the previous value, it should be the same. Yes, exactly. Here also I obtain 2675.46. Okay, so only for the quality of 100%, I can use or this table, the saturated one, or the superheated one. Okay, but for example, if the quality is instead of 100% is 90%, I can only use this table here, the table of the book. Okay, and then I will determine, depending on the quality X, knowing X, I can find H by knowing HF and HFG. We will do examples on this when I have the quality, how to get H. Okay.
Doctor, I have a question.